In 2026, SpaceX intends to transition the massive Starship program from its early atmospheric testing phase to sustained Earth orbit operations. CEO Elon Musk currently places the odds of a 2026 Mars launch attempt at roughly 50-50. This probability is not a question of vehicle construction. The stainless steel hardware for the largest rocket ever built already exists on the pad. The true bottleneck is a capability never before achieved at this scale: the transfer of cryogenic propellant between two ships in orbit. This requires moving thousands of tons of sub-zero liquid methane and oxygen between vehicles moving at 17,000 miles per hour in a vacuum. Without this transfer, the exponential mass penalty described by the rocket equation forces interplanetary payloads to be so small they cannot support a sustained human presence. Success in 2026 depends on solving fluid dynamics in microgravity. It is an engineering challenge of plumbing and pressure, occurring hundreds of miles above the launch pad. The rocket equation dictates how much fuel is needed to move a specific mass. In aerospace engineering, the payload mass fraction, the ratio of cargo to the total weight of the rocket, is the defining constraint. Starship must burn through nearly its entire propellant load just to overcome Earth's gravity. This chart tracks the propellant mass during ascent. By the time Starship reaches low Earth orbit, it is functionally empty. During the Apollo era, NASA used a direct ascent architecture. A single massive rocket, like the SLS shown here, launched its entire mission payload at once, which strictly limited the weight of the cargo that could reach deep space. SpaceX utilizes a distributed launch paradigm. This architecture relies on refueling the primary ship while it waits in orbit. A single outbound mission requires multiple tanker flights to launch in quick succession, meeting the destination ship to refill its main tanks. This logistics chain requires the rapid reuse of both the Super Heavy booster and the ship upper stage. The tankers must land and relaunch within days to accumulate enough fuel mass before the planetary alignment for the Mars transfer window closes. In this new architecture, Earth orbit serves as the critical staging ground and fuel depot for interplanetary transit. Low Earth orbit presents two major physical challenges: extreme temperature swings and the absence of weight. Starship's propellants, liquid oxygen and methane, must be kept at hundreds of degrees below zero to remain liquid. On Earth, gravity pulls liquid to the bottom of the tank. In orbit, the propellant floats erratically, breaking into spheres and clinging to the tank walls due to surface tension. This leads to the Ullage gas problem. In microgravity, the pressurized vapor bubbles used to maintain tank pressure intermix with the floating liquid. Pumping this mixture of gas and liquid into the transfer lines causes cavitation. These rapid pressure changes create shock waves that can rupture the vehicle's plumbing. Additionally, solar radiation threatens to heat the hull, boiling the cryogenic fuel back into a gas during the wait in orbit. To prevent this, SpaceX uses specialized tank insulation and rotates the spacecraft to keep the propellant tanks in the shade. Mastering this environment is the equivalent of pouring a boiling, weightless liquid into a thimble while in freefall. SpaceX's solution to the microgravity problem is the creation of artificial gravity via microacceleration. The tanker and destination ship dock tail to tail, revealing their internal header and main tanks. Small maneuvering thrusters fire, creating continuous forward acceleration. This force settles the liquid oxygen at the back of the tanks against the transfer valves. Once the liquid is settled, a pressure differential between the two ships pushes the propellant across the docking threshold. The flight computers must maintain this acceleration with extreme precision to avoid snapping the mechanical docking seal between the two vehicles. This maneuver converts chaotic, floating fluids into a predictable orbital pipeline. As the valves open, a high-velocity stream of cold blue liquid oxygen surges smoothly into the destination ship. The system must maintain a high flow rate to move the required mass before thermal leakage affects the propellant density. To make room for the liquid, the destination ship vents its internal Ullage gas into the vacuum. This thermodynamic balancing act prevents the tanks from overpressurizing during the transfer. When the destination ship reaches its capacity, the valves close and the vehicles decouple. The tanker immediately begins its return trajectory to Earth for recovery and inspection. SpaceX must repeat this high-risk sequence perfectly up to a dozen times in order to completely fuel a single deep space mission. This systematic, repeating process is what enables a massive payload capacity beyond Earth orbit. 2026 is the year the Starship architecture moves from theory to its first full-scale orbital test. Every step in the chain is dependent on the previous one. Orbital flight proves the hull, rapid reuse provides the tanker fleet, and cryogenic transfer provides the range. The timeline is governed by the 2026 Mars transit window, the brief period when Earth and Mars are closest in their orbits. A refueled Starship possesses the delta V, or change in velocity, required to escape Earth's gravity well with a heavy payload. The final phase of this process is vacuum ignition. The mighty Raptor engines fire to begin the trans-Martian injection. The success of these cryogenic tests will define human spaceflight capabilities for the next decade. Mastery of this volatile, sub-zero fluid movement in the void is the final technical hurdle for true interplanetary scale. When the propellant flows reliably in 2026, the 50-50 odds for a Mars attempt move toward a technical certainty.